Good afternoon, everyone, and thank you very much for joining us. My name is Vikram Venkatram, and I'm a research analyst on the bio team here at the Center for Security and Emerging Technology at Georgetown University. Today, I'm extremely excited that we are here to discuss the recent AI executive order's impact on bio and assessing the AIxBio policy landscape. In a moment, I'll move into the main content of our discussion and bring our panel of experts on screen, but first, let me share a few logistical points. All attendees' microphones are muted. If you're on a computer and experience any technical issues, please use the chat function at the bottom of your screen to alert us, and a CSET team member will try to help you out. Our goal here today is to have an open and engaging dialogue. So as questions come to mind while our experts get us started, please begin sharing these questions and comments in the chat, and we will do our very best to cover as many of your questions as we can. But now, getting on to the topic at hand. On October 30th, 2023, the White House released the executive order on the safe, secure, and trustworthy development and use of artificial intelligence, the executive order on AI. This executive order had lots of goals to safeguard AI, and it covered AI from a bunch of different angles. One major theme was AI's impact on bio. This emphasis came from potential concerns that AI could enhance the misuse of biotechnology and led to 4 specific bio-relevant initiatives that have already been checked off. 3 of these had a 180-day deadline, and one of them had a 120-day deadline. The 180-day deadline just passed on May 27th. So what exactly were these 4 different initiatives? 2 of them required research and commissioned reports to better understand what the risks at the intersection of bio and AI are. The Department of Homeland Security was asked to consult with experts to assess the potential for AI to enhance CBRN, chemical, biological, radiological, and nuclear risks. To achieve this, on April 29th, DHS released selected findings from their AI CBRN report to the president. The second was the Department of Defense being asked to contract a study from the National Academies of Sciences, Engineering, and Medicine to evaluate AI's impact on biorisks. As of May 6th, they have begun forming the committee of experts for the study. The 2 others focused on implementing nucleic acid screening specifically. The National Institute of Standards and Technology, or NIST, was tasked with engaging with experts on DNA synthesis review, which they have done to a 2-year cooperative research agreement on screening and safety tools currently underway with the nonprofit Engineering Biology Research Consortium. Finally, the Office of Science and Technology Policy was asked to create a framework on nucleic acid synthesis screening, which they released on April 29th. If you'd like to learn more about the specifics of these milestones, I'll put in a plug for CSET's blog post on breaking down the Biden AIEO, as well as our executive order tracker, which tracks all the major milestones requested in the executive order. But what exactly do these initiatives mean? Now what? What's been accomplished? What have we learned? And what challenges remain? To dive into all of this, let me introduce our panelists for today. Dr. Steph Batalis is a research fellow at Georgetown Center for Security and Emerging Technology. Her research examines a variety of issues at the intersection of AI and the life sciences, including how emerging technologies will impact both biomedical innovation and U.S. biosecurity. Before joining CSET, Steph was the STEM Policy Fellow at the North Carolina Biotechnology Center, and she earned her PhD in biochemistry and molecular biology from Wake Forest University. Matt Walsh is a PhD candidate at the Johns Hopkins Bloomberg School of Public Health and a fellow at the National Security Commission on Emerging Biotechnology. His dissertation work focuses on the impacts of artificial intelligence on the deliberate biological threat landscape. Previously, he was associate staff in the Biological and Chemical Technologies Group at MIT Lincoln Laboratory, and he has supported work in biosensor development, threat attribution, warfighter health, and biological data assurance. Dr. Sarah R. Carter is the principal at Science Policy Consulting, LLC. Her work has focused on advances in the tools and capabilities for engineering biology, biosecurity screening frameworks, and international norms for biosecurity. In recent years, she has supported the nuclear threat initiatives on projects related to DNA synthesis screening and the implications of AI for biosecurity, and she works on policy issues related to the broader bioeconomy as a senior fellow at the Federation of American Scientists. Previously, she worked in the Policy Center of the J. Craig Venter Institute and at the White House Office of Science and Technology Policy. She's a former AAAS Science and Technology Policy Fellow, a former Mirzayan Fellow of the National Academies, and she earned her PhD from UCSF. So thank you very much to all of you for joining us today. And to begin, let's really dive into the executive order itself and this first slew of actions that were taken. In your opinion, what is the most notable takeaway from this first round of action items? And are there any particular or potential implications that stick out to you? We can start with Sarah first, move to Matt, and then to Steph for these opening remarks.
Yeah, hi. Thanks, Vikram, and thanks to CSET for hosting this panel. I think it's a really good idea and a really good way to take stock of where we are at this point in time. I will say that we have come a long way since October, and the whole intersection of AI and bio has just there's just been an explosion of activity in the past year or so. To me, one of the things that I've tracked for many years, to provide a little bit of a historical perspective about this moment, it is the issue of DNA synthesis screening. I started working on this topic 10 or 12 years ago when it was sort of a sleepy little niche, the whole DNA synthesis screening world. Certainly the policy analysis there was a really small group of people that would think about it. And it was one of the things that I worked on back then, I was at the Venter Institute. I started work 10 years ago on the Venter Institute report on the DNA synthesis screening framework. And in particular, just how the DNA companies had implemented the voluntary HHS screening framework guidance and some of their challenges and some of those kinds of things. At that time, that report that was released in 2015, it highlighted the technical challenges and ambiguities associated with sequence screening, and it also called for a federal funding requirement that would support DNA companies that actually perform the screening. One thing I'll note is that we launched that report in November of 2015 to coincide with the kickoff of the new interagency process, the US government process to update that voluntary screening framework guidance. And that was sort of the first iteration of that updating process that was delayed for many reasons and over many years. Policymakers were distracted, dealing with other high priorities like the Ebola outbreak and things like that. So the screening framework got a little bit deprioritized for a little while. There were some advances around that time. There were investments by the US government to resolve some of the technical issues for sequence screening in that space, in particular, a program from IARPA that called the FunGCAT program that led to a lot of advances in screening tools for DNA providers. And in particular, over the last 2 years, there was a renewed push to update the HHS screening framework guidance, and which was the voluntary framework. And that has been a great process over the last 2 years. There was a really good update to that framework in October, just a few weeks before that AI executive order. But while all of those things were happening in that space, AI sort of came on the scene and kicked everything into high gear and just brought a whole lot of attention to this particular framework, this screening framework. One of the things that I was working on, I worked on NTI. I've been working with NTI, the Nuclear Threat Initiative, on AIxBio. We started a report a year ago, and we rushed to finish very quickly, interviewing experts and synthesizing ideas into a report. And among our few key recommendations was bolstering what we described as the digital physical interface, so where digital designs become biological reality. And a key part of that was DNA synthesis screening and bolstering that framework. And another part was expanding customer screening to a broader range of products and services in the life sciences enterprise. I'll say that report was launched on October 30th, very auspiciously the same day as that AI executive order. Since then, things have just, as I mentioned, there's been a flurry of activity. The OSTP policy on sequence screening did indeed come out. That was one of the 180, I think it was 180-day timeframe. Came out in April. That policy does include a federal funding requirement that institutions that receive federal funds must buy DNA from companies that screen. There's also been a lot of activity, Vikram, as you mentioned, with NIST and the EBRC, that Engineering Biology Research Consortium, that has really been a really great process and a community-wide deep dive on some of the sequence screening technical challenges that we've been talking about. And there's just been so much more attention there. And to me, it's been almost a sea change with respect to, certainly for DNA synthesis screening. I I'll stop there for now. There are several implementation challenges, and I hope that we'll get to that later in the discussion. But to me, just in taking stock of sort of where we are, I feel really optimistic and like we've come a really long way, certainly for DNA synthesis screening and, you know, as part of an overarching framework for addressing AI bio risks.
Great. So I guess I'm up next. Thank you, Vikram, and I echo kind of everything that Sarah was saying about thanks to CSET and the timeliness of this conversation. I'll just start off by saying that the views and opinions that I expressed today are mine. They're not necessarily the views and opinions of the National Security Commission on Emerging Biotechnology, nor those of the Johns Hopkins Center for Health Security. But so now hopping over to I think maybe two things that really stood out to me with this executive order. The first is that it really elevates biosecurity and kind of AI and biology to the same playing field as other areas like cybersecurity and infrastructure security that historically has not necessarily been the case, right? And so by grouping these things together, I think it really draws needed attention, right, to this area of research and also economic activity. And then I think the other thing that I thought was frankly great about this EO is that it balances, in my mind, it balances the potential benefits of these technologies with what we know as the risks today, right? And what I mean by that is that it doesn't go so far as to implement measures that I fear would potentially hinder the development of AI and biotechnologies, right? It's a step right in the right direction. It's an acknowledgement of the work that needs to be done, right? And I think the way that it is written acknowledges that there is this important balance between benefits and risk.
Thank you both. I think it's lucky that I'm going third because my comments, I think, really draw on things that both of you have said. I think, first I'd like to second Sarah's comment that we have come a long way since October. And so I think one thing that really stood out to me about this executive order, just trying to think back to where we were in October, there was a lot that we didn't know at that point and still don't know now. And there are also areas where we were more ready to take action. And so I think that one thing that I appreciate about the executive order is that it really balanced this sort of idea of there are some things that are ready to implement and maybe take action on, and there are other areas where it's important to do some more research and ask some more questions. So before implementing regulations and oversight, I think it's important to understand some things like, which risks we're actually concerned about, which safeguards are most applicable to those specific risks. And, I think like Matt mentioned, what the trade-offs might be and kind of where things stand for the beneficial applications like scientific research and innovation. And I think I second Matt's point that if we, move too quickly without really understanding some of those points, there's the chance that initiatives just won't be effective at doing the things that we actually want them to do. So I think what really stood out to me was just that this EO included those initiatives to do the studies and get more information, in addition to taking some action on implementation, for example, for DNA synthesis screening, as Sarah had mentioned, in areas that maybe we were more ready and did know a little bit more about what should come next. So I think that's one thing that I was really glad to see and happy to discuss more as we get into this discussion.
Well, yeah, so to that point, Matt sort of brought up this balance between, the benefits and the risks and trying to, strike that middle ground and make sure that both of those are assessed. And you talked about how the executive order, or a major part of the executive order, is its requests for a variety of different reports to sort of better understand the potential for AI to enhance biological risk. But what should we keep in mind as we evaluate AI's impact on biological risk? What are some of the factors that we should consider? And I'll ask that to Steph first, and then Matt, and then Sarah.
Thanks. As a starting point, I think one of the most important things to keep in mind is that AI's impact on biorisk exists within a larger context. So sort of as Sarah had mentioned too about DNA synthesis screening, that conversation was ongoing before AI came onto the screen. There are some really foundational conversations about biosecurity and biosafety that exist regardless of whether AI is used. And then there are other conversations that are really specific to the AI. So I think part of understanding this context is identifying which vulnerabilities are related to AI, which vulnerabilities are more foundational. And in some cases, some of that work on broader biosecurity and biosafety policies may address the risk regardless of AI. And then, again, in other cases, we may need to think about more targeted safeguards. I think another part of the context that it's important to understand is that bio risks can play out in really varied ways, and that there are different policy tools and levers depending on that scenario. So for example, some of the strategies that could make legitimate scientific research safer might not be the same as strategies to address maybe an intentionally malicious actor. And so being really clear about what risks we're concerned about, I think can help us to really match the right tools to the right problems. So I think that context is what I really hope we can keep in mind while we sort of evaluate how AI might impact bio risks.
Yeah, I definitely agree with what Steph was saying here, and I think that it's important when we're talking about assessing the risk, right? Ultimately, at the end of the day, the risk or the threat, right, is coming from biology, right? That is what would cause the direct harm to the human and environment, a plant, right? But in trying to understand that, right, we need to understand the impact of AI on human behavior, right? And so it's this interesting interplay of, can AI help us or help some nefarious actor do something with biology in a way that makes it more reproducible, more reliable, right? Need less time, less reagents, et cetera, et cetera. And then the challenge there is how do we roll that up into an understanding of the impact on the potential to do harm, right? So I think it's not just one thing that we're trying to measure here; it's many things, right? And oftentimes those many things are not kind of like, as Steph was saying, right, there's many different cases, right, in which this would be used, right? So it's a very multidimensional problem.
Yeah, I agree wholeheartedly with both Steph and Matt about the kind of the threat models and the need to look at that. But zooming out just a little bit, I mean, these AI tools, especially a lot of the sort of bio-design tools, those tools that have been that incorporate AI and are designed to understand or predict or design biological systems, these kinds of tools are going to be extremely valuable for pandemic preparedness and response. So in a lot of ways, the same risks that we are worried about or that come up in these contexts will be tremendously, reduced in some ways, or the outcomes, the potential, the hazard, will be reduced by these tools, and they have a lot of promise in vaccine development, medical countermeasures, all of those kinds of things. To me, what that says is that when when you're doing an evaluation of a large language model, kind of the chat bots of the world, and you're trying to figure out how it increases risks or might enable malicious actors or cause accidents or improve ideation for something bad, like that's sort of, to me, like one set of things to think about. But when you're talking about the biodesign tools and these more specialized things that are used by a more specialized community, at least right now, you really do have to think about how they will be used. It can't just be a risk kind of analysis. You do have to do a full, risk benefits, kind of analysis about what that tool will provide to the world. I think that will make it much more difficult. I mean, we've had plenty of challenges in assessing risk, for the chatbots of the world, but I think we're going to have an additional challenge with these sort of biodesign tools in trying to figure out how to properly weigh those risks and benefits. And it's, you'll have all of the challenges of the risk assessment combined with another set of challenges for the benefit side. And then, those weighting those things is going to create a challenge as well. So we just have to figure these things. These are very complicated questions. A lot of these, a lot of attention has come onto this recently, but these things are moving so quickly that it's tempting to go very fast and just to, say, oh, you can eyeball that kind of risk. Let's try to resolve it. And it does take a little bit of thoughtful analysis to really try to make sure that you don't, that you can get those benefits, without, trying to streamline them or try to eliminate all risk and that, really make mistakes.
Yeah, that's super interesting because of course, this is a really complicated issue. And I think each of you has sort of pulled apart some of the different ways in which this is a hard problem. Steph, you talked about sort of, who exactly is the actor? Is it a malicious actor? Matt, you talked about, the threat coming from biology, but also AI systems' ability to sort of affect human behavior and maybe change how humans approach these technologies. And then Sarah, you talked about these sort of different types of AI models and AI systems, like the biological design tools, and how they're different from some of the chatbots and how those can have different effects. And then also how these systems could be used to reduce risk. So understanding how complicated all this is and how the risks and benefits can kind of come from different sources, one important thing that we might need to accomplish is to kind of evaluate what the AI models can actually do, and how much of a risk they actually present. So how doable is it to actually evaluate these models? What are some of the tools that we have at our disposal to try and understand what they can do, what they can't do, and what are some of the potential challenges of the different ways that we could approach that problem? And I'll go to Matt first, and then Sarah second, and then finally Steph.
Yeah, that's a great question, Vikram, and one that I spend a lot of time thinking about. When I think about evaluations of AI tools within the biospace, I think of kind of three categories of evaluations. The first one is benchmarking, which could be more of like a multiple choice test, if you will, right? If we're talking about chatbots, right? Can the chatbot answer these questions accurately and repeatedly? For a bio design tool, it could be, can it perform some function, right? And this is assessing the capability of the AI tool outside of the context of use by a human, right? These things, there's some work out there where people have proposed data sets of questions. But I think we really need to think about, like, what are the types of questions we want to be asking and what do we want to be using the benchmarking results for, right? It could be to perhaps, suggest a capabilities-driven threshold to moving on to more extensive evaluations, especially those involving humans. Right. The second category is what I call, or what people call, I guess, human uplift studies, right, where humans are asked to do a very specific task. And OpenAI has published the results of a study like this. RAND has published the results of the study like this, where they've been asked to do a specific task. Some people have access to a large language model-based chatbot. Others do not, and then they compare those who had access to those who didn't to see if they were able to complete the task faster, better, et cetera, et cetera. And then briefly, I think the third category is red teaming. And to me, the difference between red teaming and human uplift studies is red teaming is a little bit more open-ended, right? You just specify a goal, right, which could be come up with a plan to do harm, right? And then similar to the uplift studies, you give some people access to a tool, others not, and then check to see if one group had a better success rate than the other. The last thing I guess I'll say on this, and then would love to hear from Steph and Sarah, is that because we are working with biological agents that are particularly dangerous, right? We're not actually asking anybody to go into the lab, right, and go through this entire process. And so at the end of the day, most of these studies now are evaluating the ability to come up with a plan, right? And coming up with a plan is distinct from the ability to carry out a biological weapons attack, right? And that is something that I think will continue to be a challenge that we'll need to creatively address to make sure that the results of these studies are giving us the information that we want and giving us enough information to be able to, make policy decisions or make, decisions about the potential, access to a technology to the general public. So I'll pause there and turn it over.
Yeah, no, Matt, that was a really good framing of the kind of the AI side of the evaluations, and the way that people are thinking about that. A really helpful sort of taxonomy of those studies. On the bio side, there's sort of on the bio side, the whole history of molecular biology has been a reduction of different hurdles and a decrease in barriers to make things easier to engineer. And so I feel like, from that perspective, we're a little bit used to trying to figure out, what is the net gain, the sort of enabling, how does some new technology make it easier for some, malicious actor to cause some harm, starting with recombinant DNA, synthetic DNA, CRISPR and genome editing, benchtop devices, and in that context, AI is sort of the next enabling technology. And I think that I think it's really important in the bio world to make sure that you understand what the remaining hurdles are. And, often those are not standing still either. Those hurdles are, there's a whole range of hurdles, and some of those are still coming down. And I think that this is one reason, like, a major hurdle that kind of goes unspoken is that these designs have to make the leap into reality. And that usually involves a wet lab, a real, molecular biology space that it has infrastructure and people and, all kinds of existing oversight. And so understanding not only the kind of biological technical hurdles about how hard is it, for molecular biology, to conduct and successfully implement a molecular biology project, but also what are the existing oversight in those spaces? How do these things fit into that context as well? And so I think that there's a lot of different pieces of that kind of analysis to try to go from, what is the risk, to, how will that risk be realized? And it's important to think about all of those different pieces when coming up with a real framework for the overall risk.
Yeah, I think, sort of picking up on this thread that you've both mentioned about comparisons. And I think the importance of making these assessments and evaluations in comparison to, what's possible without AI. Both to sort of come up with oversight and regulations that can address those existing biosecurity, maybe gaps, but also to really be realistic about what the risk from the AI is. So, for example, saying that a chatbot can do something is different than saying that, a chatbot in the internet can do something, or that Google can also give you certain information. So I think being really clear about what's new from AI and maybe what's not new can help to direct attention towards the not new risks that maybe need some additional work, in addition to maybe some of the new risks, so that those safeguards can be more targeted instead of overly broad or general. So I think this idea of understanding, the AI is coming into this landscape that already existed is one way to think about how we interpret the assessments and evaluations that are going to keep coming out.
Great, thank you. So one last question before we sort of transition into the audience Q&A, and reminder to the audience, please feel free to drop any questions you have into the chat. I want to pull a little bit more on this thread of, the risk that already existed compared to the risk that might be new and how those might interact with each other. And Sarah, you discussed during your opening remarks how DNA synthesis screening, it might be an important topic of conversation today that's really growing, but it's not a new topic of conversation. And it's been, discussed for a while and studied for a while. And interestingly, it's a major theme of this AI-focused executive order. So the executive order talks about the creation of this framework for DNA synthesis screening, but why exactly is DNA synthesis screening a potential safeguard? What exactly will it take to implement that in the United States? So first to Sarah, then to Steph, and then to Matt.
Yeah, well, I think it does relate to this the DNA synthesis, I mentioned that this was a recommendation also in the NTI report that we put together on AIxBio, and it really is a key bottleneck, and it's where, it's where those digital designs, where the AI part stops, and it really becomes actual, physical reality when it's turned into DNA. And I think that it is a key bottleneck in that way, but I think that it's also, it was also just something that was there already. It was a framework. It was something that was there that had some track record where we had some, effort already put in there. And it was a really good way that community was sort of ready to make those next steps. I think Steph made that point earlier, that it was like, okay, there has been work here. The DNA companies, they've already established some good, practices here. There's good guidance that's been developed. If we can just, put more oomph into that, put this federal funding requirement on it, then that would be a really good way to make it, to go to, to start somewhere.
Sorry, I think you accidentally muted yourself.
All right, well, yes. So there's something tangible and a place where you can make progress quickly. I will say there are some serious implementation challenges that still remain in that space. One of them, in my view, is customer screening. No matter how good a sequence screening system you have, when push comes to shove, almost every red flag that comes out of a sequence screening system is going to be used for legitimate purposes. People do pathogen biology all the time. And therefore, a lot of the decision making is about the customer. Does that customer have a legitimate use for that pathogen DNA? And I think that we don't have very good resources for that. The HHS screening framework guidance has a companion guide with red flag guidance and things like that, but there's very few resources about how those decisions should be made. And I think that part of the problem or a challenge for OSTP with their new policy is also that the customer screening piece of it, they are starting to engage a broader community. It's not just traditional DNA providers. It's, contract research organizations, core facilities, cloud labs, biofoundries. All of these places are going to need to get up to speed very quickly. And I think that's going to be very challenging for them. One other sort of challenge that I'll just raise is about sequences of concern. And, this is a kind of a perennial problem in the DNA synthesis screening world, and it will always be challenging because context is very important in biology. It's hard to take 200 nucleotides of DNA and say yes, this is risky or not, because it will depend on how it's incorporated into a biological system. So I know that NIST is currently working with the EBRC to put together some basic baseline standard just for compliance with the OSTP policy when it goes into effect in October of this year. And they intend to update it every 2 years to try to broaden the sort of sequences of concern that they might capture and, do shorter sequences. So, not 200 nucleotides, but test every 50 nucleotides. But that gives you even less context and trying to broaden the sequences of concern while reducing your window, like all of those things are going to be very challenging. And I will be very pleased and surprised if they can really come up with some consensus on how to move forward with that in the future.
Yeah, I think I also am really excited to see what NIST and EBRC sort of come up with and following very closely what's going on there. I think that a lot of the points that Sarah made, especially concerning the sequences of concern, kind of highlight an even bigger challenge that's sort of underlying this entire conversation, which is that it's hard to point to what's risky, both because context matters and also because biological risk kind of occurs on this spectrum. So it might be really easy to point to a bucket of things that we can all kind of agree are definitely maybe risky and maybe a bucket of things that are definitely pretty benign. But there's this middle ground that can be really challenging. And so figuring out where and how to draw that line is a really big question, not just for DNA synthesis screening, but also for things like assessments. When do we say that a model can do something that's risky? And that's also, regardless of AI, with general experimentation too. There's a lot of questions about when to say that something has crossed a threshold or crossed a line. And so I think that that's a really challenging question, even as folks are in agreement about starting to want to implement some of these safeguards, that this is an area of definitely open questions. So I think that that just shows how DNA synthesis screening is maybe a good case study or model for some of these bigger efforts as well.
Yeah, and I think I'll just say that I think it's just as important to develop and establish the processes and infrastructure for developing these policies and these safeguarding considerations, especially in recognition that technology changes over time, right? And so I think it's important to make sure that we're able to bring in, the developer communities, right? Whether it be DNA synthesis, or AI and bio tools, right? But I think it's important to make sure that that groundwork is established so that these policies can be kind of updated over time and as needed.
Yeah, thanks to all of you. And now moving to a related question from our audience, we've been asked about for those who are seeking to create evaluations of biorisk. It would be helpful to understand where some of the important decision boundaries are. And in particular, do AI systems need to be able to impact the entire process of science from the design to release to be considered risky or dangerous? Or do they just need to reduce barriers on one of the bottlenecks? For example, if wet lab skills are a key barrier, what are some of the exact lab skills that it would be bad if AI systems were able to help with? And perhaps I can ask Steph that first, and then Matt, and then Sarah.
Yeah, I think I'll kind of go back to a point that I think it was Sarah who had made earlier, that these models are developed for purposes. And that in many cases, what's tricky about dual use technologies is that one of those uses is sort of the intended helpful and beneficial use. So there are cases where, knowing the context of why a model is being asked to do something can be really helpful. So, thinking about automating labs or trying to figure out how immune systems work can have really, really beneficial outcomes, in addition to some of these outcomes that maybe we'd rather like to prevent and safeguard against. So not so much of an answer as a way to say that this is part of what makes the question really challenging, that those key decision points are often places where the outcome could be beneficial if used properly and responsibly and by folks who are trying to do so responsibly, but could also have unintended consequences if used in the other way. So happy to see if my other panelists have some better suggestions.
I guess, yeah. So I think, I want to push back a little bit on the idea of are we trying to determine if a AI tool is risky, specifically the word risky, right? Because I think risk is definitely a relative term, right? And to behavior or ability to somebody might be acceptable when somebody else it might not be, right? So I think it's really about understanding impact and understanding capability. With respect to the question about does understanding that impact on all steps matter? I think yes, it does, right? But at the same time, some of these steps in the process are more challenging than others, right? I would say it's probably easier to come up with a plan, right, than to go through and execute each of those steps in the plan, simply because one, you can do it at a computer, and the other, you need infrastructure, right? You need to get your hands in the lab to do that work, right? And so, the premise of the question is, right, where does it matter, right, where we're trying to understand this impact? And some could make the argument, right, that it's probably more important to understand the impact on those things that have a lower probability of success, right? Because if the impact there is greatest, right, it may have the most significant contribution to the overall probability of success of carrying out a plan, right? I think this is an important question for experts to discuss, right, is to understand, okay, what are the relative contributions of each of the steps needed to carry out a scenario of misuse with biology? And I think this is something that I know I think about a lot, and there, historically there are some examples in the literature, and looking perhaps back to the 2018 National Academy study, right, Biodefense in the Age of Synthetic Biology, where they discussed many of the particular barriers and bottlenecks associated with completing these tasks. Those might be things very specifically that we want to keep an eye on. And I think maybe Danny or somebody at CSET can dig up a link to that report and put it in the chat.
Yeah, actually, I think somebody just put that paper in the chat. I saw it come through. But yeah, in terms of this question about like what types of things would AI be able to convey that would be very meaningful. And it's hard to, people talk about tacit knowledge in laboratories, and about how you need to have either kind of hands-on instruction or a lot of practice to really get good at many molecular biology techniques. And a pathogen engineering project, for example, would require many types of skills that you would need to have to do it from beginning to end. And so the sort of tacit knowledge in each of those things. And it's not totally clear to me exactly what tacit knowledge is. I mean, I spent a lot of time in the lab, and and some things just worked well for me, and some didn't, and it was hard to tell why. And it's working with biology in general is just very frustrating. It doesn't do what you want it to do. But to me, there's an interesting question, especially as AI systems, these sort of frontier models become more powerful. Instead of just being a chatbot, perhaps they will incorporate, video, and other kinds of feedback and things, and if you can have some sort of AI thing that's looking over your shoulder, or that has learned, from people that know what they're doing, and then can teach people who are more novice, particular skills, like that could be, that would be really meaningful. I mean, perhaps. To me, this is not something that we'll need to have specialized studies for, because if something is useful for those purposes, they will be used. So really what we should be doing is asking people in labs already, do you find this thing useful, and in what ways? Because it's going to be the same, the same kinds of things that a beneficial actor finds useful from these tools. Those are the same ways that it'll be useful, to a malicious actor. I'll say too, like, I think that we can borrow from, these tools. One thing about them is that they're being applied not just in biology, but in a whole huge range of places. So if we have indications that these tools have become really good at conveying, improving people's skills in other kinds of places, even if it's baking bread, or surgery, or doing tattoos, or whatever it is, like all of those things have kind of apprenticeship and long learning curves. If we really start to see that those tools can reduce the time that it takes to learn those skills, then that will be meaningful in biology as well.
Thank you. And a major theme of a couple of different questions that we've been getting surround, access to information. To your point about these AI systems being able to help people learn, one of the major topics of conversation, I think, has been about sort of open source versus closed source models. How do you think about, the distinction between open source and closed source? What are some of the upsides and downsides of, controlling user access through closed source models, or perhaps publicly available models, having limited biological or chemical knowledge? And what are some of the reasons why that might not be the best approach, or why it might be a good approach? And we can start with Sarah, and then Matt, and Steph.
Yeah, I think one key thing to understand and look at the open versus closed discussion is that there's a huge range of things between open and closed. And it's not just that either you decide to release your entire source code and everything about your model totally openly, or you lock it away and let nobody use it. There are options in between. It is a very tricky situation, and it gets back to that sort of risk-benefit analysis we were talking about. A lot of these biodesign tools, people do hope that they will, be improved, that it will be applied in a wide variety of ways that maybe the original developer didn't anticipate. But there are a lot of scientific imperatives that do make open source a good solution to meet those goals, to make sure that they can be developed, to make sure the tools live on. A lot of science is a little bit transient. And if somebody leaves their lab, that tool may, somebody else may not pick it up. But if it's in an open source environment, people in the community that have found it useful can, keep it going. So there's also just, reproducibility, validation, like all of these kinds of things that are really important in a scientific context. But there are ways that you can do that without, totally releasing source code. And I'm not sure what the best solutions are, but I do think that that's a place that's very ripe for some serious brainstorming about, what is needed and what kinds of, what kind of risk. To what extent can we reduce risks by finding something along that spectrum between, open source, like fully open and fully closed?
Yeah, and I totally agree with all of that, and I think that it's important to recognize, right, that there might be multiple reasons why you restrict access to a tool. Right, we're talking about open closed source here in the context of safety, right? But it could be simply a business decision, right, to do that. And so I do agree that it's going to take some sort of creativity to understand when, right, putting access restrictions on a model is the best decision from a safety perspective, right? If that is something that is warranted at all, given a specific model. And I think Sarah did a great job summing up the pros and cons of what the result of having those access restrictions are. So I'll just leave it at that and turn over to Steph.
Yeah, I think like both of you mentioned, there are definitely pros and cons to open and closed, and there's also a middle ground. I think one thing that stuck out to me actually from reading the NTI report, Sarah, so thank you, was that no matter what the decision is, if the choice is to maybe favor either wholly or partially closing certain models, making that feasible will take some effort. Largely, a lot of these biological models that are developed in academic settings are open for the reasons Sarah mentioned of, this historical culture of open science and the collaborative nature, but also from a resource and infrastructure point as well, that maintaining and hosting and having a platform, maybe an API to have a closed model takes the infrastructure, it takes people, it takes time, it takes money. And so if the decision is made that certain models should be wholly or partially closed, I think it'll be really important for that to come with resources to actually make that possible. Because I wouldn't want that restriction to cause certain researchers to sort of leave the game because they're no longer able to keep up. So I think, regardless of who makes the decision, how it's made, I think making it feasible will be a big part of the question.
Yeah, and actually, can I jump in there? That was a really good description of some of the challenges in trying to put together a closed environment. But on the flip side, if you do make like a good API, a web interface, for example, in some ways, or you can make that tool easier to use and actually expand access. It can be a means, of making it more accessible to a bigger number of people. And I know in the global health community, they have tools like that are available open source, but everybody uses the web-based version because they've made it really nice and easy, and it can, and the person who's using it doesn't have to have a computing cluster, and it has actually made those tools more accessible. So there is a lot to be said about kind of accessibility and open and closed, and it's much more complex than open closed. There's so many kind of different options in between, but 100% will take funding.
And I think this might be a opportune time to mention the idea that when a model is released publicly, right, if it is out there, right, in the form that the developers released it, it may not pose the same harm as a further fine-tuned or modified model. I think in some legislation this is called a derivative model. Right, that derivative model may have different characteristics and contribute to risk differently than a potentially open source, right, foundation model that has been, that has been changed over time, right? And I think that also adds this added layer of complexity of asking not only what can this model do now, but does it serve as the basis for doing something that we might be concerned about in the future, and making sure we're able to, and that is something that might not actually be able to be rigorously evaluated, right? Because this is something that hasn't happened yet, right? So.
A really interesting question we've gotten from the audience sort of looks at the flip side of this. We've touched on a little bit the potential for AI systems to sort of reduce risk or provide a lot of different benefits in the biological world. And if that's the case, these can certainly reduce technical barriers, but also what are the ways in which, for job creation or for upskilling or for, the workforce of the future, what are the skills that people will need going forward to be able to use these systems effectively? In industry, what sort of positions do you think, might need people with interdisciplinary skill sets? In the research world, similar. What do you think the future sort of workforce at this intersection is going to look like? And I can go to Steph first, and then Sarah, and then Matt.
Yeah, I think that's a really exciting question, especially thinking about what would it take to maybe capitalize on some of these potential benefits that we keep hearing about. I think one thing that will be important is to have some sort of cross-disciplinary expertise in the bio and in the ML. I think, we're seeing a lot of interdisciplinary teams. I think the more interdisciplinary training there is as well will increase the chance that these tools are developed with some of the really messy scientific caveats and limitations included that, maybe the people who are collecting the data understand, or the people who end up using these tools understand. I think one thing that gets lost sometimes is that these huge databases of scientific data can make it seem very cut and dry, when in reality, there's a lot of limitations and caveats to how we collect data, how we use it, how we interpret it. And so just having as much familiarity and expertise as possible in the biological side and the ML side, I think could end up really making sure that these models are applied in ways that are useful and beneficial.
Oh, yeah, sorry, I was next. Yes, I 100% agree that I think that the future of science is going to be much more multidisciplinary, than it is right now. I finished my PhD more than 15 years ago, and I was a experimentalist, and I never learned how to do anything on a computer, and I just don't know that that's realistic anymore. I don't think that's going to be the case. And I think this is happening actually across everything in biology right now. There's a big push and a lot of investment in biomanufacturing, for example, and they're having major problems because even just the process development, a lot of the laboratory automation, some of those things are very related, and there's going to be just a huge need for people that have some familiarity with bio, but also these additional skills. And I think that it's it's going to be the people that can they'll be best prepared for those kinds of jobs, are going to be people that have done transdisciplinary projects. Fellowship opportunities would be great. All these kinds of different kinds of funding for these people. All of these things need to be put into place so that we can so that the challenges and the opportunities of the future, we can grapple with them in a really good way.
Yeah, I totally agree. Skill sets across disciplines. I think, there is a need to be able to speak both languages, if you will, right? And to communicate with folks who are doing wet lab experiments, right? And folks who are training the models, right? And I think the ability to conceptualize, right, a AI bio project or research experiment requires an understanding of, right, how the machine learning and AI works, as well as how biology works, right? Because you need to understand what data is reasonable for me to generate, right? And how am I going to represent that biological knowledge to my machine learning algorithm, right? And then your choice of machine learning algorithm might depend on what data you have, right? And how you can represent it, right? And so I think it really is, if I was, I guess, perhaps talking to somebody starting an undergraduate career saying, I want to go into AI bio, I might say, do a formal education in some bio-related field, right? And then later on, develop your computational prowess. So
I think I would just add to that. I think that was a really great description of the ways in which knowing both can be helpful. I think the only other thing I would add is I think that that gives a really good foundation also to understand that a lot of these predictions are great for hypothesis generation and sort of being able to use predictions appropriately as a way to develop and formulate a hypothesis and sort of using that to inform what next steps might be, how the hypothesis should be appropriately tested and validated in wet lab research as well. And, sort of taking that digital prediction and knowing how to establish, how good it was or how useful it was and maybe what needs to come next. So I think there's just a lot of ways in which having that background can be beneficial in multiple ways.
Well, thank you all. Tragically, we are coming up to the very end of our time here, but I just wanted to be sure to give each of you the opportunity to provide some concluding remarks for our audience on this topic. We've covered a lot of ground during our discussion today, but just wanted to leave you all with the questions. What would you like to see happen next? And really, what do you hope that the audience takes away from this discussion? What do you think the main sort of takeaway that they should come away with is? Maybe we can start with Matt, then go to Sarah, and then to Steph.
Sure. I think there's, my hopeful main takeaway is that we need to have more discussion about how or the purpose of evaluations is, like, what is the purpose of evaluations as written in policy, right? And I think that's important because it will inform how researchers or evaluators, right, design those types of evaluations, right? If we look at I think some of the legislation in California right now, right, their language says, we are paraphrasing here, right, but like we're concerned about, models that make it less difficult for people to perform an experiment, right? And is less difficult the same as increasing the likelihood of success, right? And so, like, what is it you're truly trying to measure? And I think that that's gonna, like, getting at that question will require more conversation on these topics. And so, again, thrilled to see bio in this executive order. I think there's a lot of great work that's been done in the past 180 days, and looking forward to all the great work that will continue in the next.
Yeah, I think it is a really good it is a really, one key takeaway to me is that we really do need to spend a little bit of time trying to understand that risk and also the benefits, especially for the sort of AI biodesign tools that are designed in many cases to provide benefits and will be used in the context of pandemic preparedness and response. And I think that it's going to be very important to do those risk benefit analyses. And along those lines, I'll just note that from a policy perspective, it does not make sense to only talk about the risks. NIH, NSF have put many, millions of dollars into developing these tools, and it doesn't make sense for some other part of the government to turn around and veto them. There's going to have to be some good assessment of those risks and benefits, some better coordination within the U.S. government to participate in those sort of risk-benefit assessments. But in general, I agree with Matt. I'll come back to what I said at the top, that I'm just really excited about all of the policy work that's happened, especially on DNA synthesis screening, which was, like I said, a sleepy little niche 10 years ago, and now is really moving forward quickly, and I'm really excited to see it.
Yeah, I think my concluding thought is following both of those, that only talking about risks or only talking about benefits will probably lead to really different conclusions than if we talked about them both in the context of each other. I think one place that we see this, again, is this executive order on AI, where, the idea of risk when it comes to models in bio is pretty highlighted. But there were other executive orders on biomanufacturing and biotechnology where AI was really framed as a solution to some really big challenges. So I think, to Sarah's point, if If there are money and initiatives that are only targeting risks and money and initiatives that are only targeting benefits, they might end up not being as effective or sort of canceling each other out. And so I think thinking about how we can promote and capitalize on the benefits of these technologies while simultaneously addressing and mitigating some of their risks can sort of prevent that one side or the other approach. So I think that would be my takeaway that I'd hope to leave you with, is that both of these things can be true, and that it's best to not sort of lean too far one way or the other and when it comes to addressing policy.
Well, thank you very much to our audience for joining us today. Thank you so much to the panelists for a really lively and rich discussion. We appreciate all of the audience's questions. We're sorry that we couldn't get to all of them today. We will follow up soon with details of our next event. And in the meantime, you can sign up for additional updates and learn more about CSET at cset.georgetown.edu. We hope you all have a fantastic day, and we will see you next time. Thank you.